Okay, the next thing we have to go to is an AC circuit containing a resistor. Containing only resistor. Now there's something I should have told you which I didn't tell you earlier. I should have told you earlier, but I didn't tell you. Now, much of what applies to a direct current also applies to an alternating current. But the difference between the two is the effect of inductors and capacitors. Now, when you introduce a capacitor or an inductor into an AC circuit, which you're going to be looking at in a short while, then what happens to something different begins to happen to the current and the voltage. Now, you don't find this in direct currents, in DC circuits that have got these two components, that is the capacitor and the inductor. But in an AC circuit, something begins to happen to both the voltage and the current. But of course, we're going to be talking about that. Now, the effect of resistors in an AC circuit is not different from the effect of resistors in DC circuits. It's pretty much the same thing, you see. So an AC circuit containing only resistor looks something like this. We have voltage, of course, is the one I've been drawing for you all this while. You can see we have a resistor. So in this kind of circuit, an AC circuit where we have only resistor, in this kind of AC circuit, both experiment and theory shows that the current and the voltage are in phase. So here is an example or the diagram of a simple AC circuit containing a resistor. You see? So in this kind of circuit, both experiment and theory shows that the current and voltage are in phase. Now, what do we mean by that? For two things to be in phase, it means they reach their amplitudes at the same time. So if we were to draw a graph or plot a graph of an alternating current, instantaneous current on one axis and time taken on the other axis, in an AC circuit containing a resistor, we're going to have something like this. You see? Now, if we did the same thing for voltage as well, voltage in an AC circuit, we're still going to have something like this as well. You see? So when we say these two things are in phase, that's the current and voltage in an AC circuit containing a resistor, when we say they're in phase, what we mean is they reach their peaks at the same time. They also reach their troughs at the same time as well. That's the current and the voltage are both at their peaks at the same instant of time. Instant in time, yes. Anyone you want. So in this kind of circuit, what happens is, now using Ohm's law, and of course you know what Ohm's law is, right? It is the relation, or is the law that describes the relationship between the voltage and the current in an electric circuit. So using Ohm's law, we know that V is equal to IR, right? So we call this on equation 1. So using Ohm's law here, we know that V equals IR. That is instantaneous voltage is the same thing as the product of both the instantaneous current and the resistor or the resistance in the circuit. But you know that instantaneous voltage and current are both described as I, that instantaneous current is equal to peak current sine omega t, or peak current sine 2 pi f t. Any one of them, we call this on equation 2. Also, the instantaneous value of the voltage is given as V naught sine omega t, or V naught sine 2 pi f t. We'll call this on equation 3. So now, if we put both equation 2 and 3 in 1, we're going to have something like this. So we say putting 3 and 2 in 1, we have we have V naught sine omega t is equal to I naught sine omega t r. You see, so if we want to make I subject to the formula, we can have I naught sine omega t is equal to V naught sine omega t all over r. You see, now we can cancel out. Sine omega t would take away sine omega t here. So now we have, what we have left is V naught all over r as equation 5, no, equation 4. So the peak current and the peak voltage, when we apply the Ohm's law to describe them, will give us something like this. This is how they're related, using the Ohm's law. Similarly too, if we were to replace the RMS value, I didn't even give you this before. Now, the relationship between, I did. So, in equation 4, remember that peak current is equal to 1.414 IRMS, and V naught is equal to 1.414 VRMS. So we call this equation 5. So putting 5 into 4. Now remember that the peak value of the current is equal to 1.414 the RMS value of the current, and the same thing applies to the peak voltage as well. So if we put this equation 5 into equation 4, we're going to have something like this. So we say putting 5 in 4, we have we now have, take this one, put this one there. So we have 1.414 IRMS is equal to 1.414 VRMS all over R. So this 1.414, they divide each other out, and so we have what's left? IRMS is equal to VRMS all over R. We call this one equation 6. So both equation 4 and 6, give the relationship between the current and the voltage in an AC circuit that has only resistors. So we say equation 4 and 6 give the relationship between the current and voltage in an AC circuit. So the relationship between the peak current and the peak voltage in an AC circuit using or containing only resistors. So the relationship between the peak current and the peak voltage in an AC circuit containing a resistor, or containing resistors only, is given by this equation 4. And equation 6 gives you the relationship between the RMS value of the current and the RMS value of the voltage in the same kind of circuit, AC circuit containing only resistors. Of course, there are other AC circuits that contain capacitors only. We also have those that contain, inductors only. And then we have a combination of any two of them or the three. And we're going to be looking at each and every one of that in a moment.